In section 3.3, we're going to be looking more at exponential growth. So in the last section, we focused specifically on doubling time and halving time, which is a special case of exponential functions. But now we're going to look at these equations just in general. So to give you a definition here, okay, an exponential function is anything of the form y is equal to a times b to the power of x, where b has to be greater than 0 and it also can't be equal to 1. Okay, the domain of these equations is all real numbers, and the range is anything greater than 0. So remember, domain is our x's and range is our y's. So the x's can be anything, but the y's will always be greater than 0. Okay, when that b value is bigger than 1, then the function is called a growth function. So if b is bigger than 1, then our function will be growing or increasing over time. And then when b is between 0 and 1, so if it's some sort of decimal or fraction, then the function is called a decay function, or it's going to be decaying or decreasing over time. Okay, so we have these two graphs here, which are representative of exponential growth and exponential decay. So our one on the left-hand side, where we see the increase in our data, is growth. And then the one on the right side, where we see the decrease in our data, that's decay. Okay. We see that same sort of shape that we saw with our doubling time and halving time in the last unit, where they always kind of, with the growth, start off really slow but then sort of explode over time. Okay, or with the decay, it's the opposite. They start by decreasing really quickly and then they sort of start to level off toward the end. Okay. All right, so let's investigate some patterns that we see with these exponential functions. Okay, so as we will see as we investigate exponential functions, that the patterns in the data tell specific information about the function. We're going to expand our function to include a coefficient on the variable, so this a value right here. On the variable, excuse me, the t value actually. So our function looks more like this guy right here. Okay. All right, so we're given a few different equations, and we're going to fill in the table with these equations. So I'm going to go ahead and just pull up my calculator. All right, and let's start with our first one over here. So y is equal to 4 times 3 to the power of x. All right, so our tables already have some x values pre-selected for us, so we're just going to plug these x values into our equation. Remember, for any of these exponential functions, the domain is all real numbers, so there's nothing special about these x values. They've just kind of been picked to illustrate some different things, but you could technically pick any x value to plug into one of these equations. Okay. All right, so I'll start with the -2. So we have 4 times 3 raised to the power of -2, and we get 0.44. I'm actually going to change this to, well, I'm going to write it both ways. So I'm going to do the decimal 0.44, and I'm also going to change it to a fraction just in case that might show us something a little bit nicer. I'm going to hit math and then my fraction button, and I'm going to write it as a fraction as well. I just want to see it both ways in case it might be easier to compare in one way versus the other. Okay. All right, now let's try a -1. So 4 times 3 to the power of -1. And we get 1.33 repeating. And if I change it to a fraction, you get 4/3. Okay. All right, next plug in a 0. 4 times 3 to the power of 0. That one's just 4. And then plug in a 1. So 4 times 3 to the power of 1. And we get 12. Okay. All right, so one thing that you might notice on here is that in order to go from one number to the next, and it's easiest to see in these last two, so think, what do I have to do to a 4 to get to a 12? Well, if I were just to multiply by 3, right, 4 times 3 would give me a 12. Now, just to kind of look back at the numbers in the beginning of the table, let's see if they follow the same pattern. So if we have a 4/9 and we multiply it by a 3, that is a 4/3. So that seems to follow the same pattern as well. If I take a 4/3 and I multiply it by 3, that gives me the 4. So with all of these, to get from one number to the next, all we're doing on each of these is multiplying by 3. Okay, that's this guy right here. That's what we call the base of the function. Okay, so that number that's being raised to the variable, that's our base, or that's our growth rate. That's what we're multiplying by each time to get from one number to the next. Okay, now the 4 out front, you'll notice, actually I got my yellow, the 4 out front you'll notice shows up right here. Okay, that's going to correspond to where your x value is 0. So that number out front, the coefficient in the front of this, is simply the y-intercept. That's your starting point. Okay. Kind of like we saw with our doubling time, right? We had that initial value out front, which an initial value is just a y-intercept. Okay. All right. Let's go ahead and look at our next one. This time we have 25,000 times 1.4 raised to the power of x over 10. All right, so again, we have some x values pre-selected for us, and let's go ahead and plug them in. So we have 25,000 times 1.4 raised to the power of negative 10 over 10. Okay. All right, so we have, I'm not going to bother with the fraction on this one because that's a big number. So 17,857.14. All right, and then if we plug in a 0, 25,000 times 1.4 raised to the power of 0 over 10, you get that 25,000. So again, you'll notice here that when x equals 0, we get the 25,000, which was that coefficient out front. Okay. All right, let's raise it to a power of 10. So 25,000 times 1.4 raised to the power of 10 over 10. So plugging in 10 for our x on this one. So we get 35,000. So it's growing. All right, and then plug in x equals 20, so 25,000 times 1.4 raised to the power of 20 divided by 10. And we get 49,000. Okay. All right. So let's go ahead and look at our next one. Okay. All right, so this time we have 100,000 times 1/2 to the power of x over 5. So our first x value is a negative 5. We have 100,000 times 1/2 to the power of negative 5 over 5. We get 20,000. All right, if we plug in a 0, 100,000 times 1/2 to the power of 0 over 5, we get 100,000. I think I wrote down that last one wrong. That was a 200,000 on negative 5, not 20,000. counted my zeros wrong. And this one is 100,000. There we go. So again, you'll notice when x equals 0, we get that guy again. All right, plugging in a positive 5. We get 50,000. And then plugging in a positive 10. Oops. Okay, we get 25,000. Okay, so this one you'll notice is decreasing, right? 200,000, 100,000, 50,000, 25,000. And that's because this B number is less than 1. Okay, so this would actually be a halving example because the B value is a half. So it's getting smaller as we increase our x's. Okay. Now something else that I want to point out on here, which I didn't really point out in the last one because it was tricky to see, but this one is pretty easy to see here, is that we can again see that B value, the 1/2, reflected in how our y values are increasing, right? If we take 200,000 and multiply it by our base of 1/2, we get 100,000. If we multiply that again by our base of 1/2, we get 50,000. Multiply that by our base of 1/2, we get 25,000. So for each of these, multiplying them by a half, which is our base, we get the next value. Now, this is a little bit odd because in the first one where we saw this, okay, we were just going up by ones in our x's. We were from -2 to -1 to 0 to 1, and that's where we saw that base represented multiplying by 3 each time. Whereas on this example, we're not going up by ones, so you would kind of think that you wouldn't see that same pattern, but we're going up by 5s. Okay. The reason why we still see that pattern that we multiply by the base to get from each number to the next is because of our exponent up here. Okay, notice that in our exponent we have x divided by 5. So if we count by 5s in the table, then we see that from each number to the next, we multiply by 1/2. Okay. Now, if we go back and look at the last example, which, like I said, I kind of skipped because it was a little bit harder to see here, let's just see if it holds up to the same pattern. So our exponent, we had the x divided by 10, and notice in our table, we were again counting by 10s. So we should see reflected that if we multiply each of these numbers by our base of 1.4, that we should get the next number. Let's see if it actually works out that way. So if we take, and this one might be a little off because we did round this decimal, but 17,857.14 times 1.4, that's pretty close to 25,000. And if we take 25,000 times 1.4, we get 35,000. Multiply that by 1.4, and we do get 49,000. Okay, so as long as your x values are increasing by whatever number is in your denominator up here, then you're going to see that your y values are being multiplied by the base in order to get from one to the next. Okay. All right. So let's do this one last one over here. Okay. So this time we just have a plain x up there again, which is why we're just counting by ones in our table. So let's go ahead and plug these numbers in. So let's start with 2 to the power of -2. We get 0.25. Or if you prefer that as a decimal, that would just be a 1/4. We do 2 to the power of -1. It's a 0.5. or again as a decimal, that would just be a 1/2. All right, 2 to the power of 0 is 1. Okay. So on this one, right, the reason why our y-intercept is coming out to a 1 is because there was no number in front of our base on this one. And anytime there is no number, it's just an understood 1 out front. So we are still getting, when we plug in 0, our y-intercept is the number out front. It's just that it wasn't explicitly written this time. And then lastly, if we plug in a 1, we get a 2. Okay, so again, we can see our same pattern here of if we take one x value and multiply it by our base of 2, or excuse me, one y value, multiply it by our base of 2, then we get the next y value. So we took 0.25, multiplied it by 2, we got 0.5. Multiply that by 2, we get 1. Multiply that by 2, we get 2. So we again see that base reflected here in the same way that we did before. All right, so again, we can see times 2, times 2, times 2. Okay. All right, so kind of some patterns that we noticed here. Let's go ahead and look at these questions. So it says in the exponential function y is equal to a times b to the power of x over t, the base b can be found by dividing consecutive outputs, right? And we saw that. And if we took 12 divided by 4, we got 3. If we took 4 divided by 4/3, we got 3, right? That was what we were showing here, that in order to get from one number to the next, you multiply by the base, okay? But if you don't know what that base is, then all you need to do is work backwards side. Let me just show you that real quick. If I can get my calculator to pull up. Right, so if I were to take, for example, let's look at this one right here. If I were to take 25,000 and divide it by the number before it, 50,000, then I get 1/2, which was the base of my equation. Or if I were to take 50,000 and divide it by the number before it, I would get that 0.5 again. So if you're ever looking for the base, just take a y value, divide it by the y value before it, and you can find what your base is, okay? All right, now, then we want to answer the question, in what order do you have to divide in order to get the correct bases? Okay, so that was what I was just saying. Divide, I don't know how to word that. Divide the, not the bigger number necessarily, but the second number by the first number, I guess we could say. By that I mean, like this would be my second number, this would be my first number. So I'll say divide a number by the number before it in the table. So divide the y value by the y value before it in the table. Okay. All right. Next question, where can you find the a in the table? Okay, so remember we talked about that, right? Our a value, which is that number out front, is our y-intercept. So that's always going to correspond to where x is equal to 0. So this is our y-intercept. It corresponds to where x equals 0. All right, and the last question over here, what do you notice about the change in the input values in these tables? So again, we talked about that, right? We said that what our input values is changing by depends on the t value up here. So the input values are always going to be multiples of t. input values need to be multiples of t. Okay. All right. So what we want to do on this next one, okay, first you can read through this. That says these functions are very predictable. When you have data or an application that is exponential, the function will always be in this form: y is equal to a times b to the power of x over t, where a is our starting amount, right? That's our y-intercept, or where x is equal to 0. B is the growth multiplier, and t is the amount of time it takes the growth multiplier or the growth rate to happen. Okay. A is the output when the input is 0, or the starting amount. B is calculated by dividing output 2 by output 1, as long as the change in the input is constant and t is input 2 minus input 1. Okay, so that's basically saying that our input values have to be multiples of t. Okay. In a word problem, all of these numbers are obvious. In a table of data, they must be calculated. Okay, so that's what we're going to do here, is we are going to look at this table and we're going to calculate these different values. So what our goal is on this is we're trying to find an equation in the form y is equal to a times b to the power of x over t. So we need to find our a, b, and t values. Okay. All right, so let's start with a. Okay. So just remember, a is always the starting amount. So you're looking in your table for when x is equal to 0, and your a value is just the y-coordinate right there. So in this case, we would see that our a is equal to 2. Okay. All right. Our t value, remember, is basically going to tell us how our x values are increasing. So in here, our x's are going from 0 to 10 to 20 to 30. So our x's are counting by tens, which would mean our t value is 10. Okay, that's coming from these guys over here. Right, and then lastly, in order to find our b, which is our growth rate, we just need to take one output value and divide it by the one before it. So in your head, I really didn't need to pull out my calculator for this, but if we're looking for our b, we would just take any output value, so I'll pick the last one, 16, and divide it by the output value before it. Okay, and we just get 2. So like I said, you could have done that in your head, but I just pulled out my calculator by habit because we were doing the others. So our b value in this case is 2. Right? And just to kind of look and make sure that that's consistent throughout the whole table, and if we were to take 2 and multiply it by 2, we would get a 4. If we took a 4 and multiplied it by 2, we would get 8. So that stays consistent throughout. All right, so just putting it all together then, we would get our y value is equal to 2 times 2 to the power of x over 10. Right, so I just plugged in my a, b, and t into the equation. Okay. All right, let's do the same thing for this next one. So let's start by looking for our a value again. So that's always just where our x is equal to 0. So this would be our a on this one. Our a would be equal to 24,000. Okay. All right, and then our t value is usually pretty easy to see as well. We're just looking at how are we counting our x's in our table. So from -50 to 0 to 50 to 100, we're counting by 50s. So our t is 50. And then for our b value, we just need to take an input value, or an output value, an output value, and divide it by the output value that came before it. So I'll just pick the last two again. I don't know why I like to do that. So 34,560 divided by 28,800. Let's go ahead and divide those. So 34,560 divided by 28,800, and I'm getting 1.2. All right, so let's just make sure again that this is consistent. So if I were to take 20,000 and multiply it by 1.2, I get 24,000. If I were to multiply that by 1.2, I get 28,800. So that is consistent throughout the whole table. So these are all just multiplying by 1.2. All right, so putting all of this together, we would get y is equal to our starting value, 24,000, times our growth rate of 1.2 raised to the power of x over 50. Remember that 50 is just telling us how long it takes or how many increments you have to go in order to get that growth rate. Okay, so you have to go 50 x values in order for your y's to grow by 1.2. All right, I'm going to end this video here, guys, so you can take a break and process, and then we'll do the rest of it in the next video.